Welcome back to Numerical Methods. Today we're going to start our last unit, which is initial PDEs and ODEs, so differential equations. As a start, we're going to start with initial value problems in ODEs. Over the course of the next few lectures, we'll expand that to boundary conditions, and then we'll touch on partial differential equations. So just as a review, from the last unit, we looked at integration and differentiation using numerical methods. Specifically, last time we talked about how we can get high accuracy numerical differentials using equally spaced data, using, say, the forward divided difference, backward divided difference, and central divided differences. And then we could get use extensions of that to look at unevenly spaced data using, say, a Lagrangian polynomial to interpolate the values and then take a derivative of that. And then we talked about Richardson extrapolation in terms of differentiation. Today, we're going to focus in on initial value problems to ordinary differential equations. So specifically, we're going to talk about how we can implement these methods using Runge-Kutta based ideas for single ODEs, specifically Euler's method, the Heun method, the midpoint method, and fourth order Runge-Kutta. Then we'll talk about how we can use iterations for Heun's method and some examples. So just as a reminder, ODEs come up routinely in math, science, and particularly engineering, in that we can take some sort of physical law, so say F equals ma, and then apply that law to, in the form of a differential equation, to watch how a system evolves either in time or in space. In this case, we can relate the definition of acceleration to the definition, using the definition of what that is. So that's the derivative of velocity with respect to time. And we can then put this model together. What we've done so far in most of your engineering classes and science classes is used calculus to solve these problems. But these problems can get far too complex to do by hand. And so we have to solve them using a numerical approach. So that's what we're going to talk about today. And this is likely to be, this unit is going to concentrate on methods that are likely going to come up over and over again throughout your life in engineering. So first, let's just do a brief review of ODEs. So our ordinary differential equations always have an order depending on the highest difference involved. So in this case, in our first order ordinary differential equation has this form dx dt. We can have some constants and some other values in here, but we know that it's the highest, it's a first order equation because we have only one dx dt. We don't have dx squared, we don't have anything else. We've got just that one order. We could look at a second order ODE, and we're going to know that that's a second order because the highest value here is a 2. So in this case, if we say m times d squared x dt squared plus c dx dt plus kx equals 0, this is a second order equation, even though there's that first difference in that term. Let's very briefly recall how we can solve simple ODEs from either from our differential equations class. So let's say we have an equation, right? This is the base equation that we may be trying to understand through solving ODEs. So in this case, we have this fourth order polynomial. We can put this into a differential form by differentiating the equation. Here we have dy dx equals negative 2x cubed plus 12x squared minus 20x plus 8.5. Oftentimes in science, engineering, math, in solving these problems out, we have this form of the differential equation and we want to go backwards. In order to do that, in this case, we can move this dx term onto this side of the equation by multiplying through by dx and then integrating this out. So we could say y is the integral of 2x cubed plus 12x squared minus 20x plus 8.5 dx. Right, so this is then our integration of that differential equation. When I solve this out, we get y equals negative 0.5x to the fourth plus 4x cubed minus 10x squared plus 8.5x plus c. If we look and see how this compares up at the top, it matches identically all the way up to that constant. And that constant is there because it's going to determine the solution to which we have. So if I were to put this in a graphical form, right, our ODE that true equation that we were solving for can be mapped out as this line here, at which point, at several points along these lines, we can get specific difference terms. This means when I undo that derivative by taking an integral, I end up with a family of solutions. And to fit that final C, I need to pick which of these solutions are the correct one. So in essence, we need to know some piece of information at a point that will pick out the correct solution for us, right? So if I'm picking one single point, this is going to be an initial value problem because it's going to say, add it somewhere, this is how it changes. Right, so even if I had this piece of information at this point, we're still going to call it an initial value problem, even if I end up going backwards, because all I need is that one point, which will solve for help us in selecting the correct solution from a family of solutions. So if I had a higher order ODE, maybe say in a boundary value problem, I would need to pick. I would need more information, but in a single initial value problem, we only need one piece of information. So let's specify a little bit more clearly what distinguishes an initial value problem from boundary value problems. So an initial value problem is a case where we have all of our dependent variables at the same independent variable. So in our first order case, right, if I know information here, I can solve this out. We could also have a case where I have multiple equations that I need to be solved simultaneously. Those can still be initial value problems as long as I have all of the information at the same independent variable. So as long as I have everything at x equals 0, or say for both v and x, or everything for y and z at x equals 0, right? I have to have all the information at the same point, and that will then enable me to solve that equation out. So these are called initial value problems. Think about this when I have all the information at a single point. Boundary value problems are cases where I have information at two separate points. So this is not going to come up when I have, say, just a first order equation, but this will come up if I have a higher order equation, or I have multiple points that I'm solving simultaneously. That would be the case where I have no information, say, here and here, and I'm solving for what's happening in between them, right? So these are called boundary value problems because the information bounds the solution, and we're going to talk about that in the next chapter. But for the purposes of today and the rest of this chapter, we're going to talk about just initial value problems. So let's talk about how we're going to approach solving this. So we know that we want to solve an ODE, say maybe dy dt, which is a function of perhaps y and perhaps t. We're going to approach this in a one-step method, where we're going to rearrange this equation to isolate some next value, say y of I plus 1, and it's going to be composed of a previous value, so from the previous step, so yi plus some incremental function phi that we're going to use to extrapolate, and some step that we're going to take h. So in essence, I'm going to say my next location of y is my old location of y plus some increment that tells me about the change times how big of a step I want to change by. So this is going to be the method. New is old plus increment plus step. And the first and simplest method among these method types is called Euler's method. Remember that dy dt provides us information about the slope of a point at some sort of t. So let's say I'm here on this chart and I'm at this point at ti. If I know what that derivative is, I know what that slope is, and I can project out what I'm going to be at some ti plus 1. So going back to this idea, we're going to say that this yi plus 1 is our yi times this increment function f, this increment function phi, which is f of t and I, times this step size, and I can say that that step size is h. And so let's go through and determine what my step size might be and what this increment function is. And let's do this for the this function as sort of an example of dy dt equals ky. So we're going to approach this by using our definition for what a derivative is. So remember from last time when we talked about differentiation, we said, we said that we can use a function for what our derivative is. So we can use our forward difference formula. So we can say yi plus 1 minus yi is equal to ti plus 1 minus ti. Right? And we can say that this is a valid definition for my derivative. So that still equals ky. Now, we want to put this into the form where I have this yi plus 1, maybe I'll pick a different color, that we have this yi plus 1 that's isolated. Because, right, remember, we want to get it into a form where we have yi plus 1 equals old yi plus some sort of function. So I can do this by multiplying this difference down here across the sides onto the other side. So I can do this and I get yi plus 1. So my next yi, or my next y is minus my current y is equal to ky times ti plus 1 minus ti. All right, so now all I need to do to get this into the form that I'm looking for is to subtract or add yi to both sides. So I can have ky times ti plus 1 minus ti plus yi. Okay, so now we have this form that I'm looking for. So my next step is ky times ti plus 1 minus ti plus yi. So we can remember in this form that we're sort of looking for that we have this step that we can call h, and this is that phi that we were looking for. So we can say that phi, which can be a function of y in this case, is equal to ky, which is equal to dy dt. So we don't have to go through this process of solving things out. We can just take our differential equation that we had, and that is our phi that we're looking for. So we can say di plus 1 equals dy dt times my h, so my step size, plus yi. And this is going to be my main form of the equation for Euler's method. So this is going to provide us the fundamentals. Now, before we go in and do an example, let's just look and see what might happen. So if I'm sitting at this point, maybe I'll pick a different color here. If I'm sitting at this point here, and I take this derivative, I'm going to get a straight line, right? Because I have to be getting a straight line because of this method. I'm just using the tangent. In reality, I might have this function which is going to curve. So I'm going to get some error associated with this. And the error in taking this next step is going to be, we're going to be able to break it down into several different types. The first type of error is a truncation error. And so this is the error that's going to be caused by the nature of the techniques. So this is going to be what we can control. Round-off error is that idea that we have previously talked about, where we're only considering a certain number of digits that we're using and we're writing down from step to step. Remember when we're talking about linear equations, and we said by only keeping track of a certain number of digits, we're going to end up with round-off error. Well, this can come back here. We can't really control that beyond saying, telling the computer how many digits we want to keep track of. Truncation error, though, is what we can control by selecting a proper error. The error can be further split into two pieces. Local error, and so this is the error that's going to result from each application of the equation. So maybe as a graph, remember we had this line, we then drew a tangent and we said, okay, here's our next point. But then the true line crossed. So this, at this point, would be considered our local truncation error. But now I'm sitting at this point. I'm going to maybe take a new slope and end up sitting here. This is going to be have cumulative effects as I go from step to step. So this error that's associated with here is going to propagate through my system so that by the time I'm at the end, all these local errors have added up. They don't necessarily add up linearly, right? The error sort of grows from step to step because every time I'm off, I can be off by more and more and more. So the propagated truncation error is going to be the error that results from all the error that came from previous steps. So I want to make one last comment on the error. And this is the order of the error that's going to come with our method. So the local truncation error of Euler's method is order h squared, and it's proportional to the derivative of f of y and t. This means that if the derivative is very large, my error is going to be large. If my derivative is very low, so say I have a relatively shallow derivative, I'm not going to have much error. Now, if we look at a global scale, the global truncation error is on the order of h. So once again, we're moving back to a linear truncation error. The good news, though, is that our global error can be reduced by changing step size. So as I decrease this h, I should have a better and better error. Additionally, we can say that we will have zero error if the underlying function is linear. Additionally, the method is going to be stable, conditionally stable, depending on the size of h. So if I go to small enough sizes, I won't have, I'm guaranteed not to have any instability in the method. So I'm not going to have things blow up. So Euler's method as we'll see in a second, is going to require relatively small h for a high accuracy, but it's guaranteed if we use a small enough h to give us a correct answer. Now that we've sort of talked a little bit about Euler's method and where it comes from, let's use it in a case where we have a derivative of y, so our dy dt is equal to 4 times e to the 0.8t minus 0.5y. We're going to have an initial conditions that at t equals 0 and y equals 2, that at t equals 0, y equals 2. And for this case, we're going to take a step size of 1. Just for comparison purposes, I'm providing the exact solution that you can get from solving out the ODE using differential equations, which says that y equals 4 over 1.3 times e to the 0.8t minus e to the negative 0.5t plus 2e to the 0.5t. Let's go in and use and start plugging this in. So remember from Euler's method, we say that the next y, so yi plus 1 is equal to yi plus that function of t and y times my step size. So let's go in and find out what t I'm working at. Remember, my t0, my initial t, was equal to 0. My delta t was equal to 1. So my next y, or the next t that I'm looking at, so t1 is equal to 1. So I can put down in this case y at t equals 1 is y at 0 plus my function at 0 and 2. Remember, so this was our initial t naught, and say our y naught. So we know, and then times my step size. So my dt is 1. My step size is 1. So the only thing that I need to calculate is what that f of 2 comma f of 0 comma 2 is. So in this case, remember that f just is my differential equation. So that's y prime equals 4e to the 0.8t minus 0.5y. So I just need to plug in those values. So f of 0 comma 2 is equal to 4e to the 0 minus 0.5 times y, which is 2. When I plug all of this in, I get 3. So now I can substitute this in to my equation. So y at t equals 1 is equal to 2 plus 3 times my h, which is 1, which gives me 5. Now, the true solution, remember, is y times 4.13 times e to the 0.8 minus e to the negative 0.5 plus 2e to the negative 0.5 times 1 is 6.1943. This means that we have a true error of 6.1943 minus 5 over 6.19463 times 100% equals 19.2%. So not a ton of error, but not necessarily that close either. We're going to see how this is going to end up stacking in a second when we go to do the next iteration. So for the second step, we can do sort of the same process. I can look at y of 2. Remember, this is going to be our second step. So we have our t, this is our t, equals the previous t, which was 1, plus delta t, which was 1. So this is 2. And that equals y of 1 plus f of 1 comma 5 times my h of 1. So I'm going to put this in here. So that's h. So this was t of 1, and this was y at 1. Remember, we had just calculated this. So this is my y at my previous t, so that's t1. Okay, so we can plug all of this in here, and so my previous y was 5 plus my f value, so this is just that partial differential equation that we were given, so 4 times e to the 0.8 times 1, so that's my t, minus 0.5 times y, that previous y was 5, that plugs in here, times my time step, so my h, which is 1, and I can do all of these out and I get 11.40216. Okay. You'll notice that we're putting in our previous value of y, right? So this is coming out of that rearrangement of my equation for the definition of a derivative. Additionally, I have to use the previous value of y because I don't know where I currently am, right? I've taken that step forward, but I don't know what that current value of y is, so I couldn't substitute anything else in here. So I'm using my best possible guess. We could take this and do this over and over again, doing each step out. And you'll often see these in tables. So in this case, you'll have this t going down. So each of these t's is, right, the old t plus my time step. So t plus h. And then here I've plotted the true values, and then we know we can use our Euler's method here. What you'll see is each time I take this, take a step, my error increases. So my first step had an error of 19.28. The next time, my true error is bigger at 23%, then 24%, then 24.5%. It's growing because there's local error associated with each of these steps that I'm taking. Every time I take a step, I have more and more error that's adding up. Okay, so we can plot this out and we can see how this would look. So taking that same data and plotting it, we can see that my derivative is undershooting that true form because everywhere along that length, my derivative is getting steeper and steeper, and I'm only evaluating that derivative at a certain number of points. So we're getting this increase in error. You can see then that I would have smaller error if I took a smaller time step, right? So if I instead took another time step, say here, I wouldn't have gone so far, so my local error would be better, and I would have a better estimate for what that derivative should be, and I would match the true solution better. So this is one way to get a better solution, would be to decrease that step size, and therefore increase the accuracy of the method. The other way to get around this is to use a better method. And so the first, more accurate method. And so the first way to do this would be what's called Heun's method. So remember that in Euler's method, we used a forward derivative, where we used that forward derivative. So a better guess, remember, would be coming from the idea of the central difference formula, where I could estimate the derivative between 2 points by knowing the value at a point before and a point after. However, the issue is we don't know what that next step is. What Heun suggested is, let's take the slope at the point that I know, estimate out using Euler's method what this slope at this next point would be, or what this next y value would be. So once I'm at this point, I can then take my slope here. Then he said, then I'm going to average this slope and this slope in a central difference-like formula, and take that average to be what the derivative should be over the entire length. The idea with that derivative is I should get a better estimate of my error. So let's put some math to this. So we can get a better estimate of that error by taking the average slope between my current point and then my next point. So let's put some math to that. So the first step, of course, is predicting what y is. So here we're just going to use Euler's method. So here we have that same yi plus 1 equals yi plus f ti yih. You'll notice, though, that now I have this 0 in here. So that 0 is representing that it's going to be our first guess, or 0th order guess as to what the information is at this slope. So once I have this piece, I'm going to go back. I'm going to take the information that I can say I'm guessing is happening here, and then go back to this first point. So we're going to go back to that first point to calculate a true, or at least better, y. So in this case, we have yi plus 1 is yi plus t of ti yi plus f of ti plus 1 yi plus 1 naught over 2 times h. Remember, these f's are equal to my dy dt. So that f is my differential equation form. We can start seeing that where this is really coming from is we first predict what my yi is, and then we use that information to correct that approximation. This is called a predictor-corrector approach, where I first look ahead and then use that information to go back and correct that initial approximation. Additionally, this can be iterated, right? I can do this multiple times. I can go in, calculate my yi from Heun's method, and then say, oh, does that match this initially predicted yi? Using some sort of error. If the error is large, well, I can just go in and predict again. So I can go in and just say, okay, I'm going to do this again. We can do it again and again until the approximations or the error between one step and the next is quite small. Let's see how this is going to work. We're going to still use the exact same criteria, the exact same equation for solving this. And we're going to go from time equals 0 to time is 4 with the same initial conditions and same step size. Here we're going to use a relatively tight convergence criteria to make sure that we get a really good estimate. So first we need to calculate our predictor. So what's our predicted value? So remember, the first time we go through, we use our Euler's method. So we can calculate this. So we can say that y prime, so the slope, is 4 times e to the 0, remember, because that's t at that first step, minus 0.5 times y. Remember, our initial conditions was y equals 2. And when I plug this all in, I get 3. Now I can determine my predictor at t equals 1. So we have, for my first step, y equals 0 is my old y, which was 2, plus my slope, 3, which was 3, times my time step, which was 1. And when I multiply all this out, I get 5. This is exactly what we had with Euler's method because we did Euler's method again. Here's where Heun's method is different. Now we're going to go back and we're going to correct this value. This time we're going to use this equation where I use the function value not only for my current points, which were 0 and 2, but now I'm going to input my information into this function where my ti plus 1 was of course 1, and then we just calculated our predicted y, which was 5. So first we need to go in and find what our slope is for our predicted value. So this we say y1 is equal to 4e to the 0.8 times 1 minus 0.5 times my y value, which is 5. And when I do this out, I get 6.40264. So now I'm ready to go in and make my actual prediction at y equals 1. Here we go. We have our y equals 1 is equal to my old value for y, which was 2, plus my old slope, which is 3, plus my new slope, which is that 6.402164, divided by 2 times h, so my step size, which was 1, and this ends up equaling 2 plus 4.70108. So in the end, my estimated value is 6.70108. We can see that this value is quite different than the predicted value that we had just with Euler's method. But let's look and see what my error was. So remember, my predicted value was 6.70182, 1.082, which is a true error of 8%. This is much better than the 19% error that we had with the guess of 5. However, in most cases, we won't know what that true error is, so we need to find an approximate error. So let's go in and find what my approximate error is. So remember this, we take the absolute value of my best approximation minus my previous approximation over the best approximation times 100%. This is a 25.4% error. This is way over that limit that we said we wanted to improve upon. So what we're needing to do is we need to go back and recalculate a new estimate of y1. So now I'm going to go in, I'm going to put a 2 up here to indicate that this is my second estimate. So we still take my old estimate of y0, right? Because we haven't moved on to y1 yet, which is 2, plus the average between my first case slope, remember back to 3, and here I'm just going to write out the entire equation for what my what the slope is, or what that derivative function is. So that's 4e xp to the 0.8 times 1 minus 0.5 times 6.701082. Remember, this is that new predicted value all over 2 times 1. And now we're going to get an answer of 6.2758 0.58. So now we have our new value of y1. We can see that the difference between our new estimate and the old estimate is much closer. Instead of being off by 1.7, my y is only changed by 0.5, so significantly better. We still, though, should calculate what my approximate error is. In this case, it's 6.275811 minus my old guess, which was 6.70182 over 6.275811 times 100% equals 6.776%. All right, so the error has gone down significantly, but we're not there quite yet. We can go ahead and do this one last time by hand. We can say y 1, 3 equals 2 plus the old slope plus my derivative at my value, so 0.8 times 1 minus 0.5 times 6.275811. So my best guess for y over 2 times my step size, which was 1, which gives me 6.382129. And I can do this again and again and again until I get an error, an approximate error at that step to be less than our convergence criteria. Let's look at how this compares to Euler's method and the error associated with it. So here I've written out my steps, so 0, 1, 2, 3, 4, and I've provided the true estimates. If you remember, with Euler, every single time I get worse and worse. I'm still going to get worse and worse every time with Heun's method, but I'm going to be a little bit better off. So in the first step of Euler's method, which was the first step of the beginning of the Heun's method, we had an error of 19.28%. I dropped that down using the single shot Heun's method to I get much closer to the true answer by using 6.70. So this is an error of only a true error of only 8%. I've more than halved the error associated with that first Euler step. If I go that one step farther and do iterations, I get a true value of 6.36. This is only 2.7% off of the true value of 6.19. We can see that we get much, much closer by doing that iteration. Now, you'll notice we still don't match that perfectly. I still have this 2.5-ish % error. This is because that error is just the error of that method. That's the closest that we can get based on our step size of 1, right? So even if I were to iterate out more and more, I'm going to get diminishing returns. However, this improvement in error is going to have ramifications in later steps. So if I look to latter, if I do this again for t equals 2, say 3 or 4, we can see that the true error of Euler's grows to 24.5%. With my Heun's method, my error still grows, but less quickly. in which case I reach an error at t equals 4 of only 10.62%. Going one step forward with my iterative scheme, I can decrease even further and have an error of only 3.18%. So with this, I want you to start noticing that it takes additional work, right? So I'm using more information in the Heun's method than in the Euler's method by using that approximation. And then I'm going to get even better by doing this iterative approach where I can go through and recalculate those values again and again to decrease that error. The next method that I want to talk about is the midpoint method. This is similar to Heun's method, but it's going to predict the slope at a midpoint. The idea here is instead of taking the step all the way out to this t equals I plus 1 step, I'm going to stop short at t equals I plus 1/2. I'm then going to use the slope at that line for calculating the that next time step. I'm not going to go through all the math in the example because it ends up being very similar to Heun's method. But in this case, when we take that time step for doing the prediction and correction models, we're only going to take half a time step instead of the whole time step for the prediction. But then I'm going to use the whole time step for predicting my next point. This ends up giving us a truncation error of only on the order h to the 3rd power and a global error of h squared. This is an improvement in the order of my error by h over the previous two methods. This idea of prediction correction is going to come together can be extrapolated, where we can say instead of just guessing out 1 point ahead, we could guess out potentially multiple points ahead. And in order to get our estimate for what an appropriate slope would be. These are called Runge-Kutta methods. They're going to approach the accuracy of a Taylor series without the cost. Remember, our Taylor series says our function value, say y at I plus 1, is a function of y0 plus the derivative times my spacing plus that second derivative, 1/2 that second derivative, times the spacing. The benefit of my Runge-Kutta methods are I don't need to calculate any higher order derivatives. So the idea is going to be, we're going to take as our slope, so that slope is going to be a series of constants, a's, times some sort of function where the k is going to be some sort of predicted function. So if I'm sitting at this point here, I'm going to predict forward I'm going to extrapolate several different functions. And then I'm going to take some combination of what the slopes are at each of these functions as my new slope. So in other words, we're going to say that K1 is the slope at my current point. K2 is going to be some extrapolation. So that Ti plus P1H plus comma y plus Q11 K1H. So this is a time step, and this is a step forward in space using the information from K1. Then K3 is going to be similar, where I'm going to take a different step forward in time and use an improved extrapolation in space using that K2 value. And I can keep adding in more and more constants and coefficients and get a more and more complex version. The one we're going to talk about is going to be called the fourth order Runge-Kutta method. In this case, the fourth order, what makes it fourth order, is going to be how we select these P's and Q's, and the fact that we are going to use up to K4 of them. So this is the most popular Runge-Kutta method. It is the most popular Runge-Kutta method because it's quite accurate and while still being relatively computationally inexpensive. So let's look at what that formula is. So we're still using that single step approximation, right? We have yi plus 1 equals yi, some version of a slope formula times my step size h. These coefficients, this 1/6, 1s and 2s in this equation, are the P's and Q's that are going to come, are those A's from that previous equation. Now we can go in and look at the individual K's of this case. So our K1 is going to be that just Eulerian slope. So I'm going to project outwards. But I'm only going to project outwards to half of my space step, right? This is like the midpoint method. So I'm not going to go all the way out up to this point. That would be if I went the whole distance, because we're going to think that the air is going to be relatively high by going that far out. So I'm going to only go halfway. Once I'm at that halfway point, I'm then going to calculate a new slope, K2. So what's the equation for K2? Well, my time component is the current time plus 1/2 my step size. And then I have my Euler method for my y. So yi plus 1/2 ki times h, k1 times h. Right, this 1/2 is because we're only taking half a step. And the k is that Euler's method. Once I get the slope at K2, I now have, I'm now going to go back and plug that in again. So now I'm going to come down here, and it's going to be sort of like Heun's method, where I'm going to repeat that same step. So I'm going to use this information at K2 and K1 to estimate a better slope, K2. So this is halfway between K1 and K2, and I'm going to once again go halfway the distance forward. So if I look at K3, so the slope at this point here, it's going to be my derivative equation, my derivative function, plus t at t plus 1/2 h, so because I'm still sitting at that halfway point. And my y is going to be this yi plus 1/2 K2 times h. So I'm going to use this K2, which was my average. And I'm going to put that into K3. So here I've got this piece going down, and then I'm going to finally use that in K4, but this time I'm going to extrapolate all the way to ti plus 1. So I'm going to go use a full step extrapolation to calculate K4. But I'm going to use this updated version of K3 to get the information at K4. So let's put this into practice. So the first thing that we're going to do is say we're going to use our fourth order Runge-Kutta to solve this equation. Remember, this is our f of t comma y. We're going to do this from 0 to 1 with a step size of 1. And we're going to say that we're interested in this initial value of when t is 0, y is 2. And of course, I'm going to write out our fourth order Runge-Kutta. So the first thing that we need to do is calculate our different k's. So here I've written out the equations for our different k's. So let's start with k1. So k1 is just f of t and y. So this is equal to f of 2 comma 0 comma 2, which is 4 times e to the 0.8 times 0 minus 0.5 times 2, which is 3. This is the same solution we've seen a few times now. Now we're going to go in and calculate k2. Remember, k2 is going to be located at 0.5 and 3, right? So if I look at this equation, I take my half time step and I use the, and I need to use the information from up here. So to get that y, I need to, it's not 3, sorry. I need to actually put in the equation y equals 2 plus 3 times h times 1/2. Remembering h is 1. So this equals 3.5. Okay, so I have, I need to use my Euler's method to get this value, but I can find it equal to be 3.5. And then I can plug these 2 points into the equation. So we get 4 times e to the 0.8 times 0.5 minus 0.5 times y, which was 3.5. And all of this equals 4.21729. Okay, so first step, I calculated k1. Then I used that k1 to find my y at the half step. Then I used that y at the half step to calculate my new k2. Here I've just cleaned up and made some space. Here is that 3 and that 4.21729 that I calculated on the previous slide. Now I'm ready to do this again for k3. So there's 2 steps. So the first thing I need to do is calculate y at 0.5. Well, that's just using that simple Euler's equation. We have 2 plus my slope, which is the slope for k2. So that's 4.21729, which is y, times 1/2 times my time step, which was 1. I do this all out and I get 4.1086. Now I can actually calculate k3. So that's at 0.5. That's my function at 0.5 comma 4.1086. Plug all this in. I have 4 times e to the 0.8 times 0.5 minus 0.5 times 41086. And all of that equals 3.912974. Okay, so then this is my K4. Maybe I'll box it. Now we can do the same thing for K4. I need to calculate my Y. So remember, I need to go a full time step this time. So I have Y at 1. I do this as my previous Y, which was 2, plus my K. So 3.912974 times H. So I'm getting the full time step now, which is equal to 1. So now I can punch all the numbers in. I get 9.1 5.912974. Now I'm ready to solve out for K4. That's equal to my function value at 1, comma 5.912974. This is 4 point e to the 0.8 times 1 minus 0.5 times K4, times my y value of 5.912974. I punch all of this out, I get 5.94567. Okay, whoa. So now we've solved out for K1, K2, K3, and K4. I'm ready to go in and punch all those numbers into that top equation. So written out onto this, this slide already, I've sort of collated all that math that is shown here. So I've got my K1, 2, 3, and 4 written out. I'm ready to go and solve for my slope. Remember, this is phi, so we can say phi is 1/6 times K1, which is 3, plus 2 times K2, which is 4.217299, plus 2 times K3, which is 3.912974, plus K4, which is 5.94567. Put in plus. So I do this all out, and we get 4.201037. All right, so now after all this work, I'm ready to take my actual next time step. We can say that y of 1 is equal to my old y, which is 2, plus my slope calculated out. So that's 4.201037 times my time step, which is, of course, 1, which gives me 6.201037. So we have we've done quite a lot of work. So now it's time to check our answer. Remember, my true solution at this step was 6.194631. So this means that my true error is 0.103%. So when I compare this to my simple Euler solution, Euler's method, we've gone from an error of 19% down to an error of 0.1%. This does take a lot more work than that Euler's method. However, notice that we did essentially the work of 4 iterations. If I did iterative Heun's method, after getting an error of 0.0001%, we had an estimate of an error of 3%. So even though we did less work than an iterative Heun's method, I'm still getting less error. This is coming from careful selection of these different points. So, in review, we've introduced solving ODEs. We've talked about local and global error in regards to ODEs, and then we've talked about several different ways to solve them, particularly Euler's method, Heun's method, the midpoint method, and then the 4th order Runge-Kutta method. We've also seen how we can use iterations with things like our midpoint, with things like our Heun's method, in order to solve for these values. I also want to say that while we've only talked about 4th order methods, higher order methods are available for things like Runge-Kutta. And you can increase your accuracy to any extent you want by adding more and more value to those different equations. we're not going to cover those, and we're just going to stick in this class to our fourth order Runge-Kutta methods. With that, I hope you've learned a lot about solving ODEs, and I'll see you in class.